In this video, we're going to look at the product rule, and the product rule is going to give us a rule that will help us find the derivative of functions that are multiplied together. So we're going to start off with the proof. Again, these proofs are not required learning, but it's important to see how we get to the actual rule. So let's consider 2 points on the graph of y is equal to f at x times g at x. So the graph that you see here is the product of f at x times g at x. So anytime you see a y value means we're multiplying the function f at x and g at x. So we have a y value here. That is, we've inputted the x value into f, and we've inputted the x value into g, and we multiply them together to get y. Okay. All right, so we have 2 points right here. So what we'll do is, instead of saying y is equal to f at x and g at x, we're just going to replace f at x with u and v with g at x. So another way of writing this is y, instead of saying y is equal to these two functions, we're just going to say y is equal to u times v, just to make things a little easier. So point P, instead of writing y, right, we can actually now just say, since we have this definition right here, we can say x, because that's our independent value, and y is u times v. Since y is defined as y is equal to f at x and g at x, and we have let u is equal to f at x and v is equal to g at x, so y is just uv. Okay, so we've got that written out right there. As x goes towards x plus delta x, both u and v also have to change. So as we can see that, right, you go to a different point, we've got a slight difference in x, well, we're going to also have a slight difference in y as well. Let the changes be represented by delta u and delta v respectively. So at q, the y value there is u and whatever the change is in u times v and whatever the change is in v. Since there's a change in y, which was just uv, there also has to be a change in u and a change in v, which we've represented by delta u and delta v. Okay, so now we're going to write that out. Y plus delta y is equal to, and as you can see right here, we're going to use the distributive property, uv, u times delta v, plus v times delta u, plus delta u, delta v. And we're now going to isolate delta y. Okay, so we isolate delta y by bringing this y over to the other side. We're just going to take that and move that to the other side, subtract it from both sides, and now we get negative y. Right? Well, hopefully you can see that uv, we defined uv as, right here, as y. So this right here is actually just y. And therefore, if this is just y, and we're subtracting y, these values, or these two terms, will cancel. Right? And we save that in brackets right there. Since y is equal to uv, what two terms will be eliminated? Well, the first one and the last one. So we're left with delta y is equal to u delta v plus v delta u plus delta u delta v. Okay. Now what we're going to do is we're dividing everything by delta x. The reason why we're dividing everything by delta x is because you may see this right here, that delta y over delta x is the slope. Okay? And remember, the derivative is just the slope of the function at x, but it's a very specific slope, right? It's the slope as delta x gets infinitesimally small, right? That is the derivative. So that's why we've divided everything here by delta x, because what we're going to do now is we're going to actually then let delta x get infinitesimally small, right? As q approaches p, so as we take this point and we bring it infinitesimally close to p, we notice a few things. Delta x goes towards 0. Yeah, okay, so again, we're bringing this point really, really close, right? This point q we're bringing it very, very close to P, so that we can, that secant line can become a tangent line, just like we saw in the previous unit. And if delta x is getting very, very small, if the change in x is getting very, very small, then the change in y will also get infinitesimally small. So if the change in y gets infinitesimally small, right, if this goes towards 0, then that means that the change in u and change in v are also going to get very, very small. Since y isn't changing very much, the change in the u function and the v function, because remember that we said y is equal to u times v, so the change in these functions are also going to approach 0. So note that by saying as q infinitely approaches p, we are now finding the derivative of the function, since we are looking at dy over dx, right? We've changed from big capital delta y over delta x, which is slope, and we're saying that delta x is getting infinitesimally small, so we switch to the Leibniz notation, which is dy over dx. So that's the derivative notation, right? Okay, so we're finding the derivative now. Okay, so what we have right here, if we're finding the derivative, we're saying dy dx is equal to u. Do you see that this is exactly the same thing? But now, as delta x gets infinitesimally small, this becomes the derivative of v with respect to x. And now we find the derivative of u with respect to x. So you can see that the two functions right here stay the same, but the other factor is now turning into a derivative. Note what we said right here. We said that delta u also approaches 0. So if delta u also approaches 0, then you have 0 times this derivative right here, and anything times 0 is just 0, so that final term becomes 0. Okay, we're going to now back substitute u is f at x and v is g at x. So then all we would write there is we would say that dy dx, and instead of writing u, we're now going to say f at x times and dv, so the derivative of g at x, the derivative of g at x with respect to x, plus v, which is just g at x times the derivative of f at x. Now that looks really, really complex, but it actually is pretty straightforward. If you look at this, if y is two functions multiplied together, then it is simply, let's take a look at this right here. If y is two functions multiplied together, then it's the first function times the derivative of the second, plus the second function times the derivative of the first. Okay, so if you want to write it out in words, you just say first function times derivative of second plus second function times derivative of the first. And there is your product rule. Again, this only applies if your functions are differentiable. So they don't have a vertical jump, a vertical discontinuity, or also a vertical tangent. Remember, that's also a possibility, right? If there's a vertical tangent, it's not differentiable. Or also a cusp as well, a cusp or a corner. Any one of those sharp changes in direction. Okay, we move on. So this is perfect because this allows us to see the product rule in action, right? This all that we looked at here previously might seem like very complex, like the first function times the derivative of the second plus the second function times the derivative of the first. Well, let's just take a look at an example here, okay? So as you can see, we have two functions multiplying each other. We have a quadratic multiplied by a cubic. So one of the ways of looking at this is we can just say that this right here is p at x, right? That's my first function, and this is q at x. That's my second function, okay? And I'm going to evaluate this for at x is equal to 1. So literally, the way I'm going to approach this is, as it says previously, the first function times the derivative of the second. So the first function times the derivative of the second plus the second function times the derivative of the first. That's all. That's the product rule. So let's put that together. What does that mean? Okay, well, y prime, my first function stays the same, x squared plus 3x plus 5. And now I'm going to take the derivative of the second function, and I'm going to use my derivative rules. That right there should be 3x squared. That should be 4x, and that's just 1. Okay, and then, okay, so that's this right here, the first function times the derivative of the second, plus the second function, so I leave the second function alone, times the derivative of the first. And the derivative of the first, I look at that, that's 2x plus 3. Okay, and that's it. That is the derivative of this function right here. Y is equal to this quadratic times this cubic. You see it all down here. Now I'm going to evaluate it for x is equal to 1. So I'm going to change my notation here from this notation right here, y prime. And I'm going to say the same thing is the derivative of y with respect to x, right? That's what I'm saying by saying y prime. But now I'm going to evaluate it at x is equal to 1. And all I have to do here is anywhere I see an x, I just put in a 1. So this is going to be 1 squared plus 3 times 1 plus 5 times 3 times 1 squared plus 4 times 1 plus 1. Again, which is going to be 1 cubed plus 2 times 1 squared plus 1. And then multiplied by 2 times 1 plus 3. And just evaluating all of that should give me 92. Okay, let's keep going and take a look at what we have. We have the extended product rule. Okay, now say we have 3 functions multiplied together. Well, again, if we extend this all out, we can simply see that it is just a matter of, again, first times the second, derivative of the third, first and the third, derivative of the second, second and third, derivative of the first. So we make a general rule. In general, the derivative of the product of n functions is the sum of n terms where each term consists of the derivative of one function multiplied by all the other functions. So let's just, again, take a look at this. All right. So what I'll do here is I can change these, right, into different functions right here. You don't have to if you don't want to. You can actually just go ahead and start derivating this, right? But you know, why not? Let's just change these into different functions right here. So what we'll do is we'll say that this is we'll call this one a at x. We'll call this one b at x, and we'll call this one c at x, right? Okay, so if I want to find the derivative of f at x, so f prime at x, okay, so the first two times the derivative of the third. Okay, so look, I've got the first two unchanged times the derivative of the third, right? And now what I'm going to do, and again, the order doesn't really matter here. I'm going to do the first and the third, okay, times the derivative of the second. All right, and now what I'm going to do is I'm going to do the derivative of the first times the second and the third. Okay, again, the order really doesn't matter here. Okay, so long as you have the derivative of each of these multiplied by the other functions as they are. Okay, so let's take a look at what f at x is, or what f prime at x is. Okay, so a at x, b at x, so again, I leave this alone. c prime at x, well, now I take the derivative of that. That's going to be 3x squared plus 6. Okay, and then I take a look at this. I've got a at x and c at x. So here we go. So I'll do 3 plus x, and then c at x, x cubed plus 6x. And then the derivative of this one right there, that's just 2x. Okay, and the order doesn't matter. I could have, if I wanted, I could have done this. I could take this out right here, put that in the middle. If I want to keep my a, b's, and c's, right? That doesn't really matter, right? The order of multiplication is it's commutative. So I could have kept it. I could do it like that if I wanted, right? Doesn't matter. Then derivative of the first. Well, the derivative of the first right there, the derivative of constant is 0 plus x. The derivative of x is just 1. And then b at x is my x squared minus 4. And then c at x is x cubed plus 6x. All right. And then it says do not simplify. So yeah, I'm done. Let's keep moving on. Okay, the power of a function rule is a bit of a tricky one because I'll highlight what we'll say is that we're going to derive this rule later on. So we're actually not going to look at why this rule is the way it is. We need to know the chain rule first, right? But we'll give you what the power of the function rule is. And it goes as follows. If you have, I like the function notation a little better. I think it's a little clearer. If you have a function of x raised to some power, basically you take that exponent, you move it in front, subtract it by 1, and leave the function as is. And then you have to take the derivative of the inside function. Okay? So what you do is you essentially are going to take the derivative of the outside first, then you multiply by the derivative of the inside. All right, so if you want to make a small little note to yourself right here, you can say derivative of outside first, then derivative of inside. Okay, then multiply, to say multiply by derivative of inside. Okay, so let's take a look at an example of this. Well, if I look at what my inside function is, this is my inside function right here. It's my x squared minus 3. And my outside function is this function raised to the power of 4. So let's take a look at what this rule tells us to do. Well, the rule tells us that we are going to take the derivative of the outside function first, or the light blue function first. So the outside is this function raised to the power of 4. So I bring the 4 down in front. I leave the inside function as it is. And then I do 4 minus 1, which is just 3. Then I have to multiply by the derivative of the inside function. And the derivative of the inside function is simply 2x. Okay, I'll clean that up just a little bit here. And I get 8x. And then x squared minus 3 all cubed. So again, that's the power of a function rule. And we're going to derivate this when or prove it using the chain rule, which we haven't learned yet. That'll come later. But it's important to know early on because it makes things a lot easier. So again, take the derivative of the outside first. So if there is an exponent here, bring it down. Then subtract the exponent by 1, leave the inside alone, and then multiply by the derivative of the inside function. Okay, so that right there gives us a good overview of the product rule. I think the only really challenging part of the product rule is maybe the proof. And the reality is, again, the proof you never really have to know, right? In the sense that like you will never be evaluated on the proof. It's not required for you to demonstrate a proof of this rule. You just simply have to know how to use the different rules, okay? So again, first function times the derivative of the second plus second function times the derivative of the first, Or if you have multiple functions, right, it's just a matter of going through all the different possible permutations of derivatives, right? So first and second times the derivative of the third, first and third times derivative of the second, and then second and third times derivative of the first, right? That's if you have multiple functions multiplied together. And then finally, power of a function rule, derivative of the outside first, then multiplied by the derivative of the inside. Okay, homework's listed on the bottom. Thanks again for watching.